Your services are down and you are under attack, but you can't see the enemy. The chances are DNS is under fire. So, in this video, we are dissecting the DNS packet itself to reveal the hidden mechanics behind devastating cyber attacks like DNS floods, amplification, and more. So, today we are going to cover the very important protocol that is a DNS and how the packet format look like. So, the content of this today's video is the DNS packet format, DNS query and response, and the DNS attacks, which is DNS flood, SYN flood, and the DNS amplification, and also the ransom DDoS. And followed by the live demo, I've created a few Python script so to replicate the DDoS and the SYN based attack. So before we explore the attacks, let's understand the DNA of a DNS. So every interaction, whether you are asking for a youtube.com or a facebook.com or a server is telling you its IP, it happens via these packets only. Think of a DNS as a structured message with the different parts, each playing a certain role. At the very top, we have the header section. This is like the envelope of our message. It contains a transaction ID, a unique number to match queries with their correct responses. It also has the flags, which is having a single bit that tells us very vital information, like if the message is query 0 or a response is 1. The type of operation code, or let's say opcode, and if there were any errors, it will also show in the flags itself. Those are known as responses code. Next important, the question section. This is where your computer or a DNS resolver possesses its question. It holds the queue name, the actual domain name you are asking about, like facebook.com, youtube.com, or anything. It's specifically the queue type, telling the DNS server what type of record you are looking for. It can be A record, which goes for IPv4. It can be quadruple A, which goes for IPv6, or an MX record for a mail server. And at the last, in a response packet, you will find the answer section, which contains the actual resource records the server is going to provide, like the IP address for facebook.com. So understanding this distinct part is a crucial thing because many DNS attack works by manipulating or flooding these specific section in a particular packets. Next is the DNS query format. So I have taken a snip from my Wireshark local system itself. So here's a real world example from a Wireshark of a DNS query packet. This is your computer asking for the IP address of a facebook.com. As we dissect the packet, you can see the foundational layers. The Ethernet header for a physical transmission, the IP header with the source and destination IP addresses, the UDP header, because most DNS query uses the fast connectionless UDP protocol on port number 53. But now, let's focus on the actual DNS query section itself. If you can see the transaction ID here, it's a very unique number that helps the computer match this specific query to its future responses. The flags tells us this is a standard query. And importantly, here in the question section, we clearly see the name that is a facebook.com and the type A, meaning we are asking the IPv4 address. This is perfectly normal, and that's how the legitimate DNS query look like. Next, very important is the DNS query fields. So we have a transaction ID. Now this transaction ID is very unique number to match each query or a responses appropriately. Second is the flags. Flags basically tells you if it's a query or if it's a response or if it required any recursion, etc. The third thing is the queries. Number of question that is being asked. And this is what the very important parameter in terms of DNS flood attacks. The fourth is a queue name. So the queue name basically contains the domain name which is being queried, like facebook.com. The queue type, which is a type of record that is being requested. So in our example, it is A record, which is IPv4. For mail exchange, there would be a MX record. Last but not the least is the Q class, the class of a query. Example, IN comes for an internet. That's how there are certain Q class has been observed. So let's understand what is a DNS response format packet actually look like. So a DNS response packet is actually look like as you can see on the screen. So this is what the DNS server sends back to your computer after successfully finding the IP address for a facebook.com. That means your DNS server has resolved that particular domain name for you. If you have noticed, the header flags here, they have changed. Now the query or a response bit is set to 1. That means this is the response that we have received. This also indicates that this is a response. If you can see the 1, that means it's a response. And it also shows there is no error in the response codes also. The question section is usually repeated from the original query, which confirms what was being asked. But the star of the show in a successful response is the answer section. Here you find the actual resource codes or records providing the answer to your specific query. In this case, we see facebook.com type A for IPv4, and then crucially, the actual data field containing the IP address, like for example, 31.13.78.35, like that. Along with we have time to live, which actually indicates how long your computer can cache this answer before needing to ask again. So that was the DNS response format of the packet. And if you can check the DNS response field, we have couple of fields also which look similar to the DNS query, because every DNS packet has two types, which is query and the response. So in the DNS response, we have same transaction ID, which actually matches the query transaction ID. Second is again flags. Here we are getting the response flag because this is a response packet. It can be authoritative or it can be recursion or it can be no error or NX domain also. Next, we have an answer, the number of records that is being answered. And in answer section, we have a couple of sub fields, which is one is name, that is the domain name from the query. Type, which is the type of record. Third is the class of record. Fourth, time to live, which is the cache duration. And fifth is the RD length, that is the length of the actual data field. And R data, which is the actual answer to the data. Example, like an IP address that is being resolved. So as you can see on the screen that we have a DNS flood attack. So whenever there is a normal DNS request, your client and the DNS happily communicating to each other. So your client says what is the IP of facebook.com and your DNS server resolves the actual domain name for you and it gives the response related to it. But what if I ask you multiple domain names which we have never seen, what will happen? So this is nothing but a DNS flood. So in the DNS flood attack, what happens is there are numerous and unresolved domain names which you are going to query to your domain name server. Now the actual mechanism of the domain name server is to resolve the IP address for you. But if you keep on asking the domains which never existed, your DNS will not going to give you any response. So your DNS be like there are too many requests and your DNS server will crash. And that's how the DNS flood is going to be impacted on your organization. Now, what it impacts is the CIA triad is the availability section. So here we are compromising on the availability. If your server doesn't respond to you in the meantime, it is going to crash. And did you know that the largest DDoS attack in terms of packets per second has been observed by a Cloudflare, which was 4.8 billion packets per second. And that's a really huge number. I can attach the link below and then you can have a read on it. So where does actually it impacts on the DNS packet? If you can see on the screen that the DNS packet is the query section. Now this is actually a snippet from the Wireshark, and we will see into the live demo that how this actually captures all of the data. So here you can see in the domain name system section on your left hand side, the type is E, which is the IPv4 that is being queried. And you can see we have actually going to request the random names of the domain that is being initiated by an attacker to the victim. So you can see all of the queries has been flooded, and in the packet section, the queries part is going to be impacted. And the very important thing, if you have observed, these are all the queries. So we have not received any response from the DNS server, and we are flooding all of the queries to the server, which is not good actually. Next is the DNS SYN attack. Now, this actually doesn't directly impact the DNS packet, but impacts on the TCP packets. So, a normal scenario like a three-way handshake, SYN, SYNAC, and then ACK. So here we will just say this is actually an attack which is followed by a botnets. Now, botnet is something wherein a lot of system has been compromised, and after that, they have been used to they have been used to create a SYN flood attack or any distributed denial of service attack. So here we have a SYN attack. So we are just going to send a SYN packets to the DNS server. And in between, if any legitimate user asks to initiate a handshake, will not get any response because your DNS server is actually sleeping on that moment. And where does it actually impact? It doesn't impact on directly on DNS level, as I said. It impacts on your TCP SYN packets, wherein you can see on your right hand side there's a SYN flag has been set. Now this is the SYN flag has been set, and we will see into the demo section also that a lot of SYN packets has been initiated, and there is no actually second step has been going on. So now let's talk about one of the most important and devastating and currently prevalent to the DNS attack is the DNS amplification attack. The DNS amplification attack, also known as the DNS reflection attack. Now, how it works? So the attacker doesn't hit the victim directly. Instead, they send very small DNS queries to a large number of open DNS resolver. These are the legitimate DNS servers that are unfortunately misconfigured to respond to anyone on the internet. Crucially, the attacker spoofs the source IP address in these small queries, making it appear as if the query came from the actual victim IP address. I repeat, the attacker spoofs the source IP address in these small queries, which is being queried, making it appear as if the query came from the actual victim IP address. Now, basically, the magic happens in two places at the packet level. First, the attacker manipulates the IP header of the query packet. And here in our Wireshark example of an attack query, you can clearly see the source IP is not the attacker's machine. Instead, it has been spoofed to be our intended victim's IP. So this is critical for a reflection. And the reply goes to the victim, not the attacker. Because here we have amplified the actual packet size. Secondly, the DNS question section of this query, the attacker often requests a verbose record type like any query for a common domain. And any query asks for all available records for a domain, which is designed to return a very large amount of information. So here, attacker spoofs your IP address and it asks a lot of information from your DNS. Right. So that is why it is called an any query for a common domain. So when the open resolver receives this small or a spoofed query, it dutifully responds with a much larger DNS packet. Since the source IP in the original query was spoofed, this large response goes directly to our victim itself. If you notice the stark difference in the packet size, a small 60 byte query can turn into massive 600 byte response or maybe even larger. If you dive into the DNS answer section of the response, you will see it's packet with a numerous resource records, making the overall packet significantly large than the actual initial request. So by doing this, with the hundreds of thousands of misconfigured open resolver, attacker can amplify their small efforts into an overwhelming floods against unsuspecting targets, and they can saturate their internet connection and bringing down their services completely. So let's finally reiterate the alarming rise of the ransom DDoS or RDDoS attack. This isn't a new technical term or a new technical method, but rather a chilling motivation behind a DDoS attack. Now, cyber criminals threaten organizations with a crippling DDoS attack, which could be a DNS flood, a SYN flood, or a DNS amplification. So, unless a ransom, typically in cryptocurrency or as per requested by a ransom gang, is paid. If the ransom isn't paid, they launch the attack, causing significant downtime, financial losses, and the reputational damage. Recent reports, including those from Cloudflare, confirms a significant surge in ransom DDoS activity over the past years. This highlights how the attackers are increasingly leveraging these powerful DDoS techniques, including those that target DNS as tools for direct financial extortion. So let's start with a live demo that I've created on my virtual isolated environment. So, I'm using Parallels on my Mac operating system. So I have two machines. One is um, I have one machine which is Windows machine, which you can see the IP has been set to 1037.129 and 4. This is the victim machine. And as you can see, I have created a very short script related to the DNS flood attack. So just to replicate how the DNS actually works. So before we start, I'm going to initiate the Wireshark so that we can see the live packets that is being captured. And here we are going to put the capture filters. IP source as 1037.129 and 3. I'm going to run my Python script. So as you can see, once I start the Python script, we have already started the DNS flood against our victim with 100 packets. Now this is just for an example. And as we switch to our Windows machine, you can see there are a couple of requests that is being started. And if you have noticed, this is just the query. This is just the query flag that is being queried from the actual attacker's machine. Yes, as you can see, the flags is actually set to one, which is a recursion desire. So we're going to do a completely recursions, and you can see the queries is actually the one which doesn't exist anymore, right? It doesn't exist. And this is how the response code is being received by a DNS and has been initiated by a client. So next is we're going to see how actual the plain DNS is actually looks, wherein your DNS is happily responding to and resolving the IP address for you. So I'm going to put the facebook.com on my browser, and we're going to see and awaits for the DNS packet. So in Wireshark, I'm just going to search for a DNS, and let's search for the facebook.com, which we have queried to the server. If we go a little bit of down, we'll see the start of the packet, and there you find the initial packet. As you can see, that is just below the selected one, which is a record facebook.com, and we have received the response for that also. So that one is the request one, and another one is the response one. And that's how the normal DNS queries and responses actually look like. And there you have it. We have unpacked how DNS and the attacks related to the protocol actually works. If you found this deep dive helpful, please like this video, subscribe for more cybersecurity insight, and hit that notification bell for our next episode. Thanks for watching and stay safe out there. I'll see you next video.